This is Project 21006, Coaxial UAV Tier 2.
UAVs currently on the market are either expensive, military-grade UAVs or cheaply made hobbyist-grade UAVs. The goal of this project was to develop a commercially viable rotor head assembly to fill the gap in the market. The coaxial design also offers many benefits. Safety is improved by eliminating the tail rotor, which is one of the main sources of helicopter failure. The design is also more efficient by roughly 30% and has greater performance. Our team developed 5 system requirements. From these system-level requirements, we developed 5 functional requirement categories: performance, environment, safety, interface, and design features. Within these categories, we determined the rest of our functional requirements. The system block diagram was developed early on in our project. The dotted line represents the system boundary. The external elements are power and 4 servo motors, and lift is our output.
We did 2 trade studies, one for the transmission and one for the rotor blade mounts. We went with the CVT because it varies the rotor head speed instead of varying the rotor pitch, which eliminates additional airflow complexities. It also improves the system efficiency and allows for finer control of yaw speed. Moving on to the rotor head study, our rotor heads use only 2 blades to simplify the design, minimize the number of linkages required, and be lightweight. Our design was roughly based on a smaller hobbyist drone, but we made improvements to the linkage and yaw control designs. The model uses cheap plastic links prone to breaking. Our assembly uses Heim joints to be more robust while still offering the same number of degrees of freedom. Moving on to the yaw control, the model uses a variable pitch design, but that causes less efficient and more complex airflow. Our assembly yaws using a variable speed design, where the top rotor can spin faster or slower than the bottom, which turns the UAV left or right. Our assembly is the only coaxial rotor head design to use a CVT to vary rotor speed to yaw in this way.
After the design was brainstormed and analysis performed, we produced the model in SOLIDWORKS to minimize costly mistakes. We assembled all the parts and hardware before procurement to ensure that they fit together without any collisions or interference issues. Also, since ease of repair was a core requirement, we used these models to establish quickly removable subassemblies. These subassemblies can then be worked on without being attached to the vehicle or replaced in full to allow the UAV to be put back in service as soon as possible. Once the assembly was put together, we tested the motion of the swashblade assemblies. The control of the blade angle begins with 3 servos oriented at 120 degrees around the drive axle. These servos actuate up onto the lower swashblade, which gimbals about the drive shaft and produces the same degree of tilt to the pitch connector links. This angle is also translated to the upper swashblade to achieve identical pitch for the counter-rotating blades. Before we fabricated the parts out of expensive, high-grade materials, we conducted further prototyping with cheap 3D printed parts to verify that the SOLIDWORKS model satisfied the design requirements. We found that the rotor mount clamps needed a stronger design. The rotor mounts were too big and interfered with the swashplate links, and the top swashplate needed to be enlarged to have enough clearance about the Heim joints. We tested 3 different types of belts to see what best could transmit the large amount of torque that the UAV required. The first was a V belt, but it proved to be too stiff, too tall, and too bulky. The second option was a conveyor belt, but we found it to be too rough around the edges and too difficult to work with due to the alligator clip catching on the pulleys. The third option was the serpentine belt, which offered the most optimal length, width, and height, and thus resulted in the best performance.
Our test date was April 10th. Our full assembly was put together and the subsystems were integrated. 2 days before our test date, our sponsor got called away to attend CEO responsibilities, and he informed us that unfortunately he would not be able to supply his portion of the assembly that we had originally planned on utilizing to test our design. The situation we then found ourselves in kick-started our creative problem-solving skills into overdrive. In less than 48 hours, we were able to attain an electric motor at no cost, build an entire test stand for less than $50, and develop a working controller to operate all of our servo motors using an Arduino. This is a picture of the engine we designed our entire assembly off of. This is an electric motor that we were given that turned out to be underpowered and nearly burned up. And our goal for the following week was to acquire and integrate a more powerful gas-powered engine with our existing test stand. Our circuit was run through an Arduino Uno, which we used to utilize potentiometers to move the servos. We observed our test safely from behind a wall, and in this video, the servo motor can be seen moving the swash plates and varying the pitch of the blades. This video shows the assembly functioning as intended. We were only able to run the motor for small increments as it was overheating. The RPM provided was not enough to power the system through both demonstration and analysis. Despite our issues with the motor, the rotor head assembly did run smoothly. This video shows our functioning CVT system. The servo motor was successfully able to open and close CVT pulleys, varying the speed of the rotor blades relative to each other. Here we notice that the bottom rotor blades were running slower than the upper rotor blades. Upon inspection, we found that the 3D printed bracket holding the gears in place had broken. This caused our gears to shred, as you can see in this image. However, we are confident that if this piece was machined, it would have prevented this issue from occurring. After fixing the bracket and the gears, we tested again. With the full load of the system, the motor was unable to start due to the amount of back torque of the rotor head assembly. However, the planned final design incorporates an engine starter. We decided to take the lower blades off to lighten the load on the motor. Due to removing the drag of the lower blades, the links bent and the swash plate fractured. This issue would have been solved by machining the swash plate and using all the blades in the system.
The analysis that was performed helped drive the design of our rotor blades. We were able to use provided engine specifications, such as torque and horsepower, to calculate blade dimensions, such as chord and span, by making a couple of assumptions, those being thin airfoil and symmetric airfoil. This led us to design on 2 blades per rotor with a NACA 0012 airfoil. The analysis was performed in MATLAB using lift and drag equations, as well as a little calculus to find those values. The utility of this code also provided us with the pitch angles our blades needed to produce lift. As such, we were able to reverse this code to help verify our testing on test day.
There are a total of 13 requirements that we had to verify. To name a few, we have the total blade lift, drag, the assembly weight, and the stall angle. Through the analysis, inspection, and demonstration that we were able to conduct, we concluded that our design would work. Our verification supports that with the correct motor, generator, control system, and fully manufactured parts, our design would fly as intended. By May 6th, we will deliver to our sponsors several items, such as the acceptance test plan, our SolidWorks models, and the analysis that goes with it. And lastly, we'll deliver the prototype. During the project, we overcame several challenges. Problem 1 was the feasibility of our system, given the initial engine that was chosen for the design. Our sponsor purchased an alternate engine to design around. We simplified the design, but we were not able to fabricate all of our parts, so we relied on 3D parts, which required several modifications to the design. During integration and testing, we discovered issues with the design due to the compressed timeline. We quickly responded and adjusted our design accordingly. A lesson we learned was a process that goes into an engineering design project. Another lesson was to expect problems to arise during different phases of design and testing. Despite the challenges we faced during the project, we successfully designed and built a prototype that meets and exceeds our requirements, is ready for a sponsor to move forward into a final design. Thank you for watching our video.